This is the second and final video for the chapter discussing alcohols and phenols. In this video, we will further explore another way to make alcohols, this time with a special reagent called the Grignard reagent. Then we will discuss how to protect alcohol functional groups when doing reactions that are sensitive to the presence of alcohols. And lastly, we will end the video by discussing reactions with alcohol, in particular, the oxidation of alcohols. As a reminder, last time we talked about how to make alcohols, like for example, how to make them from reactions of substitution or reactions with alkenes. We also learned how to reduce carbonyls by hydrides in order to make alcohols. And so this next reaction that we will discuss is very similar to that last one, the reductions of carbonyls. This method I'm about to introduce is called the Grignard reaction. For the Grignard reaction, you need a Grignard reagent. To make a Grignard reagent, you take an alkyl halide and react it with magnesium. So the Grignard reagent has the magnesium wedged between the alkyl group and the halogen. The most common you will see Grignard reaction is with alkyl bromide, for example here, but you can also do it with alkyl chlorides. Let's dive a little deeper into the Grignard reagent. The Grignard reagent is special because of the bond between the carbon and the magnesium. Remember that magnesium is a metal in group 2A, so it's not very electronegative at all. So even carbon is more electronegative than magnesium. Because of this, the carbon atom withdraws electron density towards itself. In fact, the electronegativity difference is so large that you can consider this bond to be ionic. So we can represent the Grignard reagent with a negative charge on the carbon connected to the magnesium, like so. Now, since it has this full-on negative charge on the carbon, so this carbon will act like a carbanion, a negative carbon. So much so that it will act like a strong nucleophile or a strong base. All right, let's go to the whiteboard to see how this Grignard reaction works. Like we said, this Grignard reagent can be represented as a carbanion with the lone pair and a negative charge on the carbon. And like how we just said that this carbanion will serve as a nucleophile, so therefore it will do a nucleophilic attack towards the carbon of the carbonyl, which is the electrophile. So upon the nucleophilic attack there, that carbon cannot accommodate any more electrons, so it will break the carbon-oxygen pi bond, the carbonyl double bond, kicking the electrons towards the oxygen. Notice that this step creates a new carbon-carbon bond highlighted there in red. And also as a result of this, the lone pairs are on the oxygen, giving us our alkoxide ion. With this alkoxide ion, we can do a proton transfer step by adding water, giving us our final product, the alcohol. Notice again, I've drawn in red the new bonds that were created in this reaction overall. And we can represent this reaction generically with the addition of the Grignard reagent as an R group, so that we can see that overall we've added an R group to the carbon of the carbonyl, and the oxygen of that carbonyl becomes your new alcohol. So if you started with a ketone, you would end up with a tertiary alcohol, and if you started with an aldehyde, you would end up with a secondary alcohol. And if you started with an ester, you also end up with a tertiary alcohol. But it turns out the Grignard reagent, the carbanion group, will be added twice. All right, let's go back and summarize this reaction again. So it's a two-step process, and physically, you have to write 1 and 2. It does not happen in one single mixture. You have to do one step, and then you have to do a second step physically. And so the first step is reacting that Grignard reagent with your carbonyl, followed by a second step of adding the water to protonate the alkoxide ion. This second step sometimes is known as a workup. If you're just adding water or maybe acidic water to protonate a charged intermediate, that's called a workup. And then so overall the whole process will give you your alcohol. This is what our Grignard reactions look like. And remember how I said we need a separate step to add the water at the proton step at the end? That's very similar to the same reason why we do that to the LAH reduction mechanism. It is because if we have water in the reaction mixture in one single step, the Grignard reagent will actually react as a base with water, deprotonating water to form your alkane, which isn't the target of the reaction. But because the pKa of alkane versus that of water is so different, this reaction is driven completely to the right, and you would have consumed all of your Grignard reagent. So because we don't want to waste our Grignard reagent, we must react the Grignard reagent first with the carbonyl and then add in water for the pronation step. And so because of this, care must be taken when you are doing this reaction to have an environment free of water. So you would use solvents like anhydrous ethers, anhydrous meaning without water, right? So you will use anhydrous ethers. All right, so that's how we use Grignard reagents to make alcohols. For our next segment, we will discuss the protection of alcohols. Remember that we just learned how Grignard reagents are sensitive to moisture, sensitive to water, and due to the fact that water and alcohol have similar pKa's, we also have to be careful when using reagent in the presence of alcohol functional groups. Let's illustrate this point with an example. Let's say you have this alkyl halide that you want to make a Grignard reagent. However, this alkyl halide also has an alcohol group. So you do that and you think, okay, that's my Grignard reagent and I'm gonna add it with my carbonyl, then in water, then voila, so I have my diol, right? In fact, that does not happen because this hypothetical Grignard reagent cannot be formed. It is unstable, it will react with each other, and so for consuming it immediately. And the reason is Grignard reactions and alcohols are not compatible. Let's see why. Remember that BRMG can be deleted for simplicity, and so the lone pairs are on that carbon at the end. And so the reasons why alcohols are not compatible with Grignard reagent, because remember the pK of alcohol is very similar to the pK of water. So if a Grignard reaction will do an acid-base reaction with your water, it will also do an acid-base reaction with your alcohol. So upon that reaction, all you get back is that simple alcohol and it's no longer a nucleophile. So you basically have wasted, consumed your Grignard reagent. So if you have an alcohol in your Grignard reagent, it is not compatible. And in fact, that brings me to a previous slide. Remember how we can react Grignard reagents with ketones, aldehydes, and esters? Well, what happens if you were to react it now with a carboxylic acid, which is also a carbonyl? So remember that a carboxylic acid is an acid. It is going to react with a Grignard reagent in an acid-base fashion rather than in a nucleophile fashion. So you have your Grignard reagent. It's going to do an acid-base reaction with the acidic proton on the carboxylic acid, resulting in creating your alkane, which is not how Grignards are useful. So because of this, we just say that Grignard reagents are not compatible also with carboxylic acids. Let's say you did want this reaction and you wanted to make a diol out of it. How can you go about doing this with a Grignard reagent? The key here, remember, is that since the alcohol is being attacked by the Grignard, we must protect it from reacting. So let's talk about the protection of alcohols. It is a three-step process where first you protect your alcohol group, blocking it so the Grignard reagent cannot see it anymore. And then you form your Grignard reagent and reacting to attack a carbonyl to form your alcohol. Once you form your new alcohol with your Grignard reaction, then you may go ahead and deprotect the alcohol, removing the protection group, right? Notice how we have created that diol that we wanted in the beginning, but it takes 2 extra steps to do so because of that incompatibility with the alcohol already present on your molecule. So how does this protection reaction work? The first step is to react it with trimethylsilyl ether, so that alcohol goes ahead and attaches itself with this trimethylsilyl group. You can abbreviate that group as OTMS. And this reaction requires that you have to have a base also. So the base of choice is triethylamine, ET3N. Let's go to the board here to quickly draw out this mechanism. So what happens is you have a nucleophile in the lone pair of your oxygen, which will do a SN2-like backside attack on this silicone and kicking out this chloride, giving you this protected alcohol intermediate. And following that, you'll have your amine working as a base to depronate and neutralize that charged intermediate, giving us our protected alcohol group. So this alcohol group is now protected as OTMS. All right, so at this point, I also want to take a moment to go back and discuss that backside attack. Some of you might be wondering how was that possible? That's very similar to an SN2 backside attack of a tert-butyl group, which, if you would recall, is not possible. That region is too crowded, is sterically hindered. However, if you replace that central carbon atom with a silicon atom, it is actually possible. And the reason for that is because the silicon atom is much larger. Because it is much larger, the bonds are a little bit longer, so there's actually more space there for a backside attack. It's not too sterically hindered. All right, so this is why that reaction is possible. And finally, your TMS group can later be removed with acid or a fluoride. And oftentimes the source of this fluoride is known as TBAF, TBAF, tetrabutyl ammonium fluoride, which has this molecular structure. All right, so let's recap on the overall process. First, you have the alkyl bromide with that alcohol group. So you want to protect that alcohol group. So you add in TMS chloride, trimethylsilyl-chloride, with a base, ET3N, triethylamine. So you form this alcohol-protected alkyl bromide, which you can then form your Grignard reagent by adding magnesium. Then, once you have your Grignard reagent, you can react it with a carbonyl and then pronating that with water to form your alcohol. Once your reaction is complete, you can then deprotect using TBAF or acid to reform that protected alcohol. Alright, so that wraps up our discussion of the Grignard reactions. Now let's move on to see how alcohols can react. And like in the previous videos, we will start this discussion by reviewing some of the things learned from a previous chapter. As you may recall, tertiary alcohols can be turned into alkyl halides in an SN1 fashion. And so let's quickly review that. If you add in HBr, it will do a proton transfer, giving you your oxonium ion intermediate. Now that we have water as a good leaving group, it will so leave, giving you your stable tertiary carbocation. And since you have that Br anion floating around, it can now do a nucleophilic attack into that carbocation, giving you your alkyl halide. Okay, so that's one reaction. And if you have primary or secondary alcohols, that's not going to work because the carbocation resulting from the loss of the leaving group is too unstable. The reaction actually can occur via SN2 instead. So again, here we start with a proton transfer followed by the direct SN2 attack of that bromide anion, giving you your alkyl halide. So that's how you would make an alkyl bromide, really. The best way to make an alkyl chloride, you would need something else. To do so, you would need zinc chloride working with HCl. And the reason for that is that the zinc cation is required to make the OH a better leaving group. Okay, so let's look at the mechanism. First, what happens is instead of that proton transfer, your oxygen will do a nucleophilic attack on the zinc, which is your Lewis acid. So that zinc now is coordinated with that oxygen. So it almost looks like that water, which was a good leaving group, but instead of water, it is even a better leaving group because that zinc further stabilizes the lone pair upon nucleophilic attack from the chloride anion. All right, so at the end, it'll give you your alkyl chloride. So these reactions are nice, but it's far from ideal because we have to use very strong acids, HCl and HBr. We don't want to use these strong acids because they can cause complications. For example, if we have acid-sensitive functional groups on our molecule that we don't want to mess around with. And also when it introduces a carbocation, you are prone to rearrangements, which leads to products that you don't want. So is there a better way? Well, remember there was a better way. So now let's turn our attention to using tosylates and mesylates. So recall that if you add in tosyl chloride along with the base pyridine, which converts the OH, which is a bad leaving group, into an OTS, which is a good leaving group. Once you have a good leaving group, you are already set to do an SN2 attack, so you would just need a nucleophile, and we'll do a backside nucleophilic attack. There is another way to convert primary and secondary alcohols into alkyl halides. The first way is to make alkyl chloride. Again, this just adds more tools in your toolkit when you do synthesis problems, right? So this new tool is adding SOCl2 and pyridine to form alkyl chloride. And the second one here is to add PBr3 to create alkyl bromides. Again, so overall, the process is to turn an alcohol with SOCl2 and pyridine into a alkyl chloride. The first step is that SOCl2. The alcohol attacks that sulfur electrophile, kicking up the pi bonds to the oxygens. That's very similar to our carbonyl examples we've seen already. And so in the same way, the lone pairs on the oxygen kicks back down, reforming your double bond, and this time kicking out a good leaving group, the chloride. Then at this point, the pyridine can come in to deprotonate, making your molecule neutral. So at this point, you have your chloride anion floating around. It does an SN2 backside attack, kicking out that good leaving group, forming your alkyl chloride. All right, now let's do this again. So again, the first step is the lone pair on the oxygen attacking that electrophilic center, the phosphorus atom this time, kicking out the bromide anion, again, which is a good leaving group. At this point, now you have created another good leaving group that is part of that oxygen. Since that bromide anion is around, it then can come back in and do a backside SN2 attack, kicking out that good leaving group containing your oxygen, therefore giving you your alkyl bromide. All right, continuing with the theme of reactions of alcohols, we start off with reactions we have already learned, which is elimination. If you recall back in the alkene chapter, we have seen that we can make an alkene by reacting the alcohol with a concentrated sulfuric acid to give you alkene and water. Again, let's go over the mechanism. You have your alcohol. It first does a proton transfer with your acidic water. Now that you have a good leaving group, it then leaves, giving you your carbocation, at which point your water can come in and deprotonate, doing a beta elimination step, forming a carbon-carbon double bond, giving you your alkene. Remember that this will give you the more substituted alkene, your Zaitsev product. Remember we learned in the previous video how to make alcohols by reducing carbonyls? In this segment, we learned the reverse of that, whereby we react alcohols with an oxidizing agent to produce carbonyls. So let's first start with a primary alcohol. Remember, a primary alcohol means then you have two hydrogens connected to that alpha carbon. If you oxidize it once, meaning replacing one hydrogen bond with an oxygen bond, you will get an aldehyde. Notice that there's another hydrogen still available, so you can oxidize it one more time. If you oxidize it one more time, you get a carboxylic acid. Notice from this step to this step, you're adding one more bond to oxygen and then another bond to another oxygen. So from a primary alcohol, you can go to an aldehyde and to a carboxylic acid. If you start from a secondary alcohol, however, there's only one hydrogen to be replaced. So if you oxidize it, you only get a ketone. You can't replace that carbon-carbon bond. You can only replace a carbon-hydrogen bond. So if you are a secondary alcohol, you stop at a ketone. And lastly, what happens if you're a tertiary alcohol, meaning that you have no hydrogens connected to that alpha carbon, the carbon connected to the oxygen? In this case, you can't oxidize it, so there is no reaction if you try to oxidize it. So the most common oxidation reagent is chromic acid. So you can make that when you add chromium trioxide with acidic acetone, or you can use sodium dichromate with aqueous sulfuric acid. The common name for chromic acid is called the Jones reagent. I am not going to require you to know this mechanism, but I will just introduce it to you nonetheless. So in this reaction, you start out with your alcohol and your chromic acid, forming what is known as a chromate ester. This chromate ester then is attacked by a water molecule, where that water molecule extracts that proton in a beta elimination type reaction, forming a carbon-oxygen double bond. So that's your oxidation step. So let's say if you were a primary alcohol and if you use a Jones reagent, it will oxidize your primary alcohol all the way to carboxylic acid. There's no way of stopping that. But let's say you want to stop at a aldehyde from this primary alcohol. How do you do that? So the answer is don't use the Jones reagent. We're going to use a weaker oxidant. So we're going to use what is known as PCC, or pyridinium chlorochromate. So again, if you have your primary alcohol, if you add in PCC with dichloromethane as your solvent, it will stop at the aldehyde. Even though there's one more carbon-hydrogen bond, it will not oxidize that further. All right, so PCC looks like this, is a pyridine ring with that chlorochromate. Now, if you have a secondary alcohol, it can only oxidize once. So it doesn't matter which one you use. If you use PCC, it oxidizes to a ketone. If you use Jones reagent, it also oxidizes to a ketone because there's no more oxidation possible. All right, so it turns out chromium reagents are toxic and horrible for the environment. So we have alternatives we can use. I'll cover two of them here. The first one is called the Swern oxidation. It is basically using dimethyl sulfoxide, DMSO, and oxalyl chloride. Again, this chapter, I'm not too keen on you knowing these mechanisms, so we'll just discuss them briefly here. So first you have your DMSO. The oxygen on the DMSO attacks the oxalyl chloride, breaking the double bond and kicking those electrons up onto the oxygen. The oxygen then kicks it back down, reforming the double bond, kicking out this time the chloride ion. So that chloride ion then now goes and does a nucleophilic attack on the sulfur. And so we have here chlorodimethyl sulfonium ion, which is the active oxidant. So your alcohol will do a nucleophilic attack on the sulfur of that ion, followed by a proton transfer from a base, triethylamine. Now, the triethylamine again does a proton transfer, this time from the hydrogen on the carbon of the sulfonium ion, resulting in this carbanion. So this lone pair on the carbon then does an intramolecular elimination step, taking away that proton, forming that carbon-oxygen double bond and kicking out that leaving group. In that step, you form this carbon-oxygen double bond, so your ketone. All right, so that's how you would oxidize the alcohol using the Swern oxidation. All right, so as a review, if you have an alcohol, you use the Swern oxidation, it would do the oxidation once, stopping at the aldehyde, just like PCC. The next more environmentally friendly reaction to oxidize alcohols is a Des-Martin pyridine oxidation, DMP. This has the same effect as the Swern oxidation. This oxidation reaction requires a non-acidic environment and doesn't require high temperatures, unlike the previous chromium-based oxidation reactions we have seen. Right, so let's say we have this primary alcohol. If you add in DMP and your solvent dichloromethane, you will get your aldehyde. Again, it stops at the aldehyde, so it just does oxidation once. So if you have a secondary alcohol, it will give you your ketone. So this is what DMP looks like. All right, so let's do a example problem. Let's say if you have this molecule, can you predict the product if you add in chromic acid? Okay, so recall that you have a secondary alcohol, so that will just convert to a ketone. And then you have this primary alcohol, what would that go into? That's right, it will do it twice, it will be a carboxylic acid. And then you have this aldehyde, so that will also become a carboxylic acid. Okay, so that's how Jones reagent will transform this molecule. So let's finally end this chapter by taking a look at how nature uses reducing and oxidizing agents, since we're talking about that so much in this chapter. So one example is NADH as a reducing agent. And the structure of NADH has different modalities. It has a base, this adenine. It has this sugar, the ribose. It has a diphosphate link and another sugar. Now, what is the important part of this reducing molecule is the reactive center outlined here in orange. So this reactive site of NADH acts as a hydride delivery agent. So again, you have that hydrogen that is going to do the nucleophilic attack. And it is helped by the fact that it is resonance stabilized by that lone pair on the nitrogen. So the nitrogen lone pair kicks in, the double bond also rearranges and fully releases that lone pair on that hydride, attacking a ketone, for example. And upon acid-base reaction, you would have reduced your ketone into an alcohol. And also at the same time, resulting this product no longer NADH, but it loses the hydride, so it is now more positive. All right, so it's now NAD+. It has a formal charge 1. Now this NAD+ is now an oxidant, so it does a reverse reaction. right? So instead of turning a ketone into an alcohol, it can turn an alcohol into a ketone. So what happens is you have that base, it attacks and deprotonates the hydrogen on the alcohol, forming that double bond, the carbonyl double bond. And with the help of enzymes, this alpha hydrogen attacks back into the NAD plus molecule, giving you your ketone and NADH back. So this NADH and NAD plus interconversion plays a key role in metabolism. It is important in what is known as the citric acid cycle or the Krebs cycle or the TCA cycle, which is basically a series of oxidation reactions that converts stored energy in carbohydrates, fats, and proteins into energy, which, let's take a step back, is a whole big topic that you will learn if you take other classes like biochemistry. All right, so we will end here. This wraps up our chapter on alcohols.